This is a pendulum. It is a known physical constant that a pendulum with a period of approximately 2 seconds has a length of approximately 1 meter. Using the formula, period equals 2 pi times the root of the length over g, which is gravity. We determined through the process of trial and error that this period is indeed 2 seconds, meaning that the length of the pendulum is indeed 1 meter. So what we did is we just did this, and then we shortened or lengthened the rope, and then we marked a new line onto the rope to determine at what point this length is equal to 1 meter.
To find temperature for experiments, we took capillary tubes, closed one end. This way we can measure the temperature for the sound wave experiments with this handmade thermometer. And then we added a drop of oil that will be rising or shrinking as the temperature changes.
So now we have obtained our ice and water that's going to be close to 0 degrees. We take our thermometer and put the bottom of it into the ice and water. We let it sit there for about 2 minutes so the air under the drop of oil will shrink and the drop of oil will go down. Now we're going to mark the placement of the drop of oil, and it'll tell us whether the environment is colder or warmer.
In order to create a 0-degree environment for measuring speed of sound, we added water to ice and inserted the tube in there and then measured the sound frequency and wavelength at each nodes. So here's an example of us conducting the experiment using the 430 Hz frequency. We used a tone generator and audio amplitude in order to ensure where the nodes are forming, in which we would be able to hear the maximum sound. We then poured water into the graduated cylinder until the maximum sound is heard. Then using the ruler we made, we measure its length. This is how we calculated the values. When used 440 Hz sound frequency, after measuring the length, we kept pouring water to see if another node is formed. It did not form, so in this case, it formed the first harmonic. A node would be formed on the surface of water, and antinodes will be formed just like the diagram. Since the length that we measured, which is 18.5 centimeters, the wavelength of the sound will be 18.5 times 4. Then we can calculate velocity of the sound by multiplying frequency and wavelength.
By using a column of water and having a frequency at one end, we were able to form a standing wave, and by changing the height of the air column in the tube, by adding water, we were able to adjust until we were able to focus on a certain harmonic of the frequency. From this, we were able to find the size of and order of each harmonic, and from that we were able to calculate wavelength, which combined with the frequency, which we know from the emitter and Firefox, we were able to get the speed of sound. This was then averaged to give our final result, and the uncertainty was simply the standard deviation of the individual speeds of sound divided by the number of terms we had there, which would have been root 3.
Before doing the experiment, we again place the thermometer that we made and see if it is at 0 degrees. The oil is aligned to the marker, so we can continue on to experiment. We experimented using a tube open on one end and closed on the other end. Since sound waves are also called pressure waves, as the sound travels through the tube, the baby powder will oscillate and we will be able to see where the nodes are forming. So here's an example of one of our trials. We used sound frequency of 262 Hz, and we noticed that the baby powder is moving towards the end of the tube and stays there after a while. Thereby, at this frequency, it would form a first harmonic with the node in the closed end and antinode on the open end. We measure its length and record the data. We repeated it several times and then tried another frequency of 790 Hz. This time, we could see that the node is forming almost halfway of the tube. We again measure its length. This time we would measure from the first node that would form on the closed end and the node that is being formed right now in the middle, almost halfway in the tube.
This experiment was conducted by forming a standing wave in a tube filled with baby powder. At the nodes of the standing wave, the baby powder was actually moved around very violently and very obviously by the interference of the waves, and therefore we were able to measure the distance between nodes and find the wavelength. From the wavelength, we were able to then calculate the speed of sound, and this was then averaged to give our final result. The error was simply calculated as the standard deviation of each result for the speed of sound divided by the square root of the number of results. In this case, that would have been 5.
First, we want to make sure that we're doing the lab in a 0-degree environment. Here's the thermometer we've made before, and we have marked where the oil drop is when the bottom of the tube is in ice-water mixture. So now if the oil drop can match the marking again, we know that the environment is at 0 degree. Now we have removed our hand, and let's wait and see if the oil can match the drawing again. It does match, so the environment is at 0 degree. Now we are trying to put two phones 4 meters away from each other, and we measure the 4 meters using the meter stick that we've made before. We've turned on Fifox acoustic stopwatch on our phone, and my friends are going to clap one at a time. The first clap will start both the stopwatches, but since the girl is the sound source, her stopwatch will be started first. And the second clap will stop both the stopwatches, and since the boy is the sound source this time, his phone will be stopped first. So one stopwatch started early and finished late, and the other one started late and finished early. So the difference in time intervals recorded by their phones will be the time it takes for the sound to travel twice the distance in between them, which is 8 meters. Now we'll go record their time intervals. And we will repeat the same trial for a couple times.
Knowing the distance that sound would have to travel in a set interval would give us the speed of sound. For our case, we had the start and stop times, and we also had the distance. This let us calculate the speed of sound here, and it was simply averaged to give our final result for the speed of sound. Its uncertainty was calculated simply by taking the standard deviation of our speed of sound values and dividing by the square root of the number of terms. In this case, that would have been 17.
So we have a phone, and it's emitting some amazingly drawn sound waves. My art skills are amazing. And the sound waves are hitting the ground, bouncing back, and echoing back to the phone. So here we have the equation displacement equals velocity times time. Here's the distance between the phone and the ground. So the velocity is therefore equal to the displacement over the time. And this means that the speed of sound is equal to twice the distance over the time of the echo. Now, why is it twice the distance? Because, well, the sound has to bounce off the ground and back to the phone because it is an echo, which means that the displacement is there and back, or twice the distance.
This experiment will use the sonar tool. You'll begin by entering your target distance, and then you will hold your phone that distance away from the ground without any obstructions in between. Use the fancy meter stick in order to measure this distance. When you are ready, push the play button and your device will emit a series of beeps. You should then use the pick data tool in order to find the spike that is between 300 and 400 meters per second, which will be your speed of sound. The distances were chosen to match the graduations on the ruler we made. We used a thermometer to measure the outside temperature and confirm it was 0 degrees.
This is 1 meter.
By timing the time it took for a sound wave to hit a wall and echo back, we were able to find the speed of sound simply by calculating displacement over time. This was repeated for multiple distances and 3 trials each. To find the speed of sound per distance, we then averaged them and found a speed of sound value for each distance. These were then averaged again to give our final value for the speed of sound, and its uncertainty was again the standard deviation of all of the speed of sound values divided by the square root of the number of values. In this case, that would have been 21.
So here are the results. Although there is a noticeable downwards trend, overall the data is still very good because the slope of the line is only 0.044, which is very minimal. The error bars are also reasonably sized as well. We finished up with the speed of sound being equal to 344.92 meters per second, with an uncertainty of plus minus 0.61 meters per second.
So this is our setup with the spring hanging from the ceiling and the Firefox app on the phone. So first we indicated that the environment's temperature is 0 degrees with a thermometer that we created with a tube and an oil drop in it. This tube was immersed in ice and water, which is close to 0 degrees previously, and marked, and the placement of the oil drop was marked. So we left the thermometer in our environment for 2 minutes and the drop did not move. So we can conclude that the environment is 0 degrees. So now we're finding the acceleration from a specific height that we're releasing the spring from every single time to find the maximum acceleration, maximum velocity of the simple harmonic motion. Now we have a frequency being generated by our phone being oscillated, and there is a frequency history right at the bottom to detect the maximum frequency. So here we have our setup with the spring oscillating back and forth, creating a Doppler effect when the frequency is detected here. So to find the Doppler effect with this formula of the moving source, first we had to find the acceleration, and obviously the acceleration is a simple harmonic one. So we use the acceleration with Firefox to find the acceleration of the source moving. And since it's a simple harmonic motion one, we can use this formula. And with the period of the acceleration that we have, if we divide the acceleration by period, we get the velocity. And we know the max frequency from the frequency history, we know the frequency from the source, and now we know the velocity, which goes here, and we can find the velocity of the sound.
To find the speed of sound from using the Doppler effect, we first needed to find the maximum velocity of the source and also the change in frequency. The change in frequency was simply given by one of the analyzers in Firefox, and the maximum velocity was found by integrating the acceleration curve by modeling it as a sine curve to find its maximum velocity. These values were then put through the Doppler effect formula to give us a speed of sound value right here, along with an uncertainty that was propagated using traditional error propagation for multiplication.